Continue with our study of thermodynamics by discussing the first law of thermodynamics. The first law of thermodynamics is actually a statement of the conservation of energy. Well, how does conservation of energy play in thermodynamics? Well, what is heat? Heat is a form of energy. Now, when you supply heat to an object, now particularly let's talk about gases. If you heat a certain amount of gas, have you experienced that the amount of gas will expand? When you drive your car for some time, the air inside the tire gets very hot and the hot air expands. You see, the pressure, the tire pressure increases as a result of that. Now, when you boil water with a lid on top of the container, when the water begins to boil, the lid begins to move up and down. Why? Because the steam, which is a gas, expands, and the expanding gas can do work. Now, what does this mean? It means heat can be converted to work. Well, heat is a form of energy which can be made to do work, and work will in turn be converted to heat. Now, there is an equivalency. Conservation of energy is satisfied in these conversions, and the first law of thermodynamics actually deals with the relationship between work and heat. Now, the first law of thermodynamics is a statement of the law of conservation of energy, which describes the behavior of systems when heat is either added or removed from the system. Now, heat added to a system can result in two things. What are the two things that heat can do to a system? We have talked about at least one of them. Heat added to a system can increase the internal energy of the system. Is that right? So it increases the internal energy of the system. We will use U for the internal energy, and therefore delta U will represent the change in the internal energy. A certain amount of heat supplied to a certain amount of gas will increase its internal energy. It also results in the system doing work. We will represent W for work, and delta W will be the change in the amount of work. So, when heat is added to a system, that can increase the internal energy, and also it can result in the system expanding. When the system expands, it does work. So these are the two things that heat added to a system can do. If delta Q is the quantity of heat added to a system, then we can say this delta Q results in an increase in internal energy delta U and a change in the system doing work delta W. That means this delta Q equal to delta U plus delta W. Now, this is the statement of the first law of thermodynamics. In other words, it is a statement of the conservation of energy. The total amount of heat added is a measure of the increase in the internal energy plus the work done by the system. Now, this statement of the first law of thermodynamics establishes a direct relationship between heat and mechanical work. You see, the Industrial Revolution actually started when scientists established this relationship, the relation between heat and work. You see, a lot of mechanical work that we can now get heat to do for us. We drive an internal combustion engine. It is a heat engine. Heat doing work for us. steam engine which was discovered by Stephenson long time ago. Actually, he observed the movement of the lid of a cooking pot as the water was boiling. Then he said, if steam produced by boiling water can do this work, we can put it to good use. And that is the evolution of the locomotives. You see how our lives can be made easy. We moved from the horse and cart era into the time of trains and cars and so on because of this relationship between heat and mechanical work. And so you can see the part played by the first law of thermodynamics in our lives is enormous. Now, this statement suggests that mechanical energy can be converted to work and vice versa. Work done will produce heat, and heat can produce work. One can be converted from one form to another. While W is a measure of the work done by the system, when you supply heat to an object, W represents the work done by the system. Negative W is a measure of the work done on the system. Now, what is an example of work done on the system? Work done on the system can result in heat generated. Now, have you ever used a pump, a bicycle pump? As you keep pumping, what you are doing is you are doing work on the gas. You see? And if you are holding the barrel, you can see the barrel gets very hot. The work done on the gas becomes heat. So, one more time, if work done by the gas is positive W, then work done on the gas will be negative W. I want you to distinguish there. The internal energy U is a function of the state of the system. We have been talking about the three different states of the system: pressure, volume, and temperature. In fact, internal energy is actually determined by these states of the system: pressure, volume, and temperature. In fact, you can add the internal energy along with this so that the state of the system is now described by pressure, volume, temperature, and internal energy. So when a gas is compressed, if you compress a gas, its pressure will change, its volume will change, its temperature will change, its internal energy will change. In the same way, if you allow a gas to expand, its pressure will change, its volume will change, its temperature will change, and its internal energy will change. So all these four are connected together. They are now the states of the system. Now, for a small quantity of heat dQ added to a system, the first law can now be written as dQ equal to du plus dW. This is the same equation. We earlier wrote delta Q equal to delta U plus delta W. You can write this using differentials. Remember, differential of a quantity is a small change in the value of that quantity. So dQ equal to du plus dW is the same statement of the first law of thermodynamics. Let's do a simple problem. If 1.68 times 10 to the 6 joules of heat energy is added to a gas that expands and does 800 joules of work, what is the change in the internal energy of the gas? Well, this is a direct application of the first law of thermodynamics. A certain amount of heat added will do two things. It increases the internal energy and it does work. Alright, so we've got delta Q or dQ is 1.68 times 10 to the 6 joules. That is the amount of heat added. dW, the work done on the system, is the work done by the system. Alright, dW equal to 8 times 10 to the 5. And we have dQ equal to du plus dW. So the system does 800 kilojoules of work. 800 kilojoules is 8 times 10 to the 5 joules. Now therefore, what is du equal to? du equal to dQ minus dW. That will be 1.68 times 10 to the 6 minus 8 times 10 to the 5. And that is 8.8 times 10 to the power of 5 joules. So, of all this heat that is added, this much is made into useful work. The system does this much work, and the rest of the heat increases the internal energy, so that the first law of thermodynamics, the conservation of energy, is satisfied. Okay? Another example where mechanical energy can be converted to heat energy according to the law of conservation.